All right, so welcome back. Today we're going to finish up on hashing and then move on to the next major topic of this course, which is graphs and graph algorithms. Last time we talked about hashing that you basically have an array, but how you put things into the array and how you retrieve things from the array is performed using this easily computable, efficiently computable hash function. You take an object, you have a hash code available to it, and then you throw it through a hash function. That gives you the index at which you store it. Right? But we also saw that there were potential problems with this. Something could be occupying that space in the array, right? Once we put 4 in here, everything that we put in after ended up with a collision. And so the resolution, that's called a collision, the resolution of that, at least initially, was open addressing. That what we did is this guy is full, so let's just go ahead and go next door and find if that's available. And that was. Well, the problem was, when we hit that same collision before, then we had to go over and over and over until we found an open spot. Right? And you can see quickly that once your hash table is full, then it becomes no better than a regular old array, an unsorted array. And so there's this kind of a trade-off here. An alternative to open hashing is closed address. Well, actually, let's go ahead and continue with the notes here. I'll go ahead and copy over everything that I've got so far. You can wrap around. One other piece of detail here is that we don't add on to the end, but instead we can wrap around to the beginning again simply by taking that mod function. This is going to be mod 8, so 50 mod 8, that takes you back around several times and then somewhere else in the table. Right? So if the hash table is full, then you need to deal with that somehow, right? Because we can't fit anything else in. If you want to support deletion of elements, that's an even more complicated project prospect because you have to, if I put 5 in there with a particular hash value, but there was a collision and I ended up locating it somewhere completely different in the array, then I went ahead and found it and then deleted it. How do I know that 5 is still in that hash table or not, right? I have to keep track of 5 was there at some point. It just wasn't where you would normally find it. It was, because of collisions, it was placed over here. So basically what you end up doing is every time you use a cell, you mark it as used. It's called a dirty bit. That this cell has become used at some point, and so you make it dirty. So that if it becomes unoccupied at some other point, you know that, it was dirty, so something existed there before, and there might have been a collision, so I'm going to have to continue probing the entire table. Right? And of course, once your hash table could be completely empty, but all the bits are dirty, in which case you don't know if it's in there or not, right? And now it's even worse than just having a regular old array, because there's nothing in there, and yet you're spending a linear amount of time to search through it for something that potentially doesn't even exist. Right? So as the table gets fuller and fuller, collisions are much more likely. The performance starts to go down and degrade into linear performance for everything, for retrieving, for searching, and for deletion, right? And for insertion. Everything becomes order n. So one alternative there is what's called chaining. Right? So chaining is where, and it gets its name from a chain, a linked list, basically. Instead of probing for a new available cell, you store multiple elements at the same location / index. Right? To facilitate this, you establish another data structure. It could be a linked list, and that's where the chaining gets its name, linked list, or a tree, etc. It could be a balanced binary search tree, etc., etc. So facilitate. There we go. There we go. Or it could even be another hash table if you really wanted to, but then what's the purpose? You've got a hash table of hash tables. You've got a two-dimensional hash table. Why didn't you just make a really, really large array, right? If you've got an n by n hash table, you might have well just had made one single array of size n squared, right? But the other ones do offer some sort of a benefit in that they can grow arbitrarily without you having to worry about the space that it occupies. And again, to visualize that we won't go over the full details here, but just to visualize it, you could have a hash table like this, and instead of storing an element, you have a reference to another, say, linked list. Right? There's the head of a linked list, and then there's there's a whole bunch of chain links here going all the way down. Right? Now, the next time that you've got a new element that hashes to this location, what do? You just go ahead and append it to the end of the linked list or to the beginning. It doesn't matter. Hopefully you're keeping track of both ends. So you could go ahead and add it to the end, and that's going to end up being order 1. Right? You're just adding and adding and adding and adding. Right? What happens, however, when all of these become full linked lists, right? Dot, dot, dot. Right? It's full there, and dot, dot, dot. In other words, you've got, say that there were n cells before, and that each one of them occupies n elements. Is that really any different than a regular old linked list? All you've done is taken a linked list of size n squared and split it into n parts, giving you linked lists of size n. Now, searching a linked list of size n, adding to a linked list of size n, searching a linked list of size n, and deleting from a linked list of size n. That's all going to end up devolving into order n, right? So it doesn't solve your problem, it just kicks it off, right? It's kind of like, excuse me, taking a linked list and making it more efficient by cutting it into 10 pieces and dealing with them in parallel. You still have order n operations. It's just that it's 1/10 of whatever n was before. And do we care about these constants sitting out front? No, it's still going to end up being linear. So you can cut it down as much as you want by some constant, by splitting them out into different tables, but at the end of the day, it's still going to be order n. Now you could, instead, as an alternative, hang off not a linked list, but something else. A binary search tree, a balanced binary search tree. In which case, now everything becomes not order n, but order log n. That's even better, right? But, again, it's going to be 1/10 log n, and that's not as good as order 1, the amortized cost that we would really like out of our hash table. So chaining itself is not a solution in and of itself, I should say. Right? There's a question? No? Okay. Again, you could do it could be a linked list, or it could be a balanced binary search tree, etc. Instead of probing, the element is added to the secondary data structure. Again, linked list, whatever. Right? But if you insert a lot of things, this just makes it some fraction of order n or order log n, right? Which is still order linear or order log n, logarithmic. So what we ultimately need is to rehash, right? Rehashing. At some point, the performance will degrade, right? Degrade. With more and more elements, all the cells become, the array cells become full or dirty. That they were used at some point, or the secondary, if you don't use probing, if you use chaining instead, or the secondary data structures become large, right? And giving you order n performance. Right? To resolve this, we rebuild a new hash table. New, larger hash table with a new, different hash function. By the way, we didn't go over the details, but when I gave you that hash function, I consciously chose values that were, let's see, let's go back over here. So tell me, what about 7, 3, and 8? What's the commonality, at least of 7 and 13? They're primes, right? What if I had chosen it to be, say, 2, or at least not relatively prime to my modulus over here? 2k plus, say, 0. What will I always be mapping to? Even numbers, right? In which case, I'm skipping over every other cell no matter what. If I went 2k plus 1, or any odd number for my additive value there. Now I'm only doing even cell numbers, or cell indices. Choosing primes means that you're going to automatically be relatively prime to this thing over here, which means that you're going to be aperiodic. Well, it's going to be periodic no matter what, because this is, of course, finite. This is a finite set. So eventually you're going to wrap around. But it guarantees that the period is as big as the modulus here. That there is some value such that every cell gets hit at some point. Right? We want our hash function to be on 2. If it's not on 2, then you are ignoring some fraction of the codomain. Right? Yeah.
So that's why you chose 7 and 13, is because would they be like relatively prime to?
They're prime, so they're going to be relatively prime to anything. Doesn't matter what the size of the table is. They're going to be relatively prime to anything. Right? Just like choosing the A to be 65,337 or whatever it was with RSA, that's guaranteed because it's prime. It's guaranteed to be relatively prime to whatever value you come up with the totient. Right? You don't have to think about it, right? You don't have to come up with something that's relatively prime or not. Okay, so go back over here. So to resolve this, we build a new, larger hash table with a new hash function. And we rehash every single element to this new table. Right? That's going to end up being order n. But it is a one-time, or at least infrequent, cost. Remember, we are on Piazza, although and YouTube. So if you have any questions, go ahead and post there. Yeah, go ahead.
If we're rehashing so that we can avoid like multiple things mapping to the same point in the hash table, I guess one assumption we're making is that if we make the hash table grow, that won't make any of the things we've already hashed like come to the same, like.
Not necessarily, right? Rehashing is necessary because you're using a brand new hash function. It could be located somewhere completely different in the new table.
Right, but it would two things we've already hashed before would never like suddenly.
You could still have collisions, right?
Oh.
Rehashing to a new, larger table does not guarantee no collisions. In fact, just the opposite. You are eventually going to have collisions because of the pigeonhole principle, right? If you've got a finite array, and you start putting things in, eventually you will have a collision because you can only fit, if it's of size n, you can only fit n things into it. Right? So you could end up still with collisions, and you'd have to have a collision resolution, right? But over the lifetime of the data structure, the amortized cost of operations, that is when you take the average cost, is nearly order 1. Right? And presented that graph last day or Monday, I guess it was, where these are going to be very expensive spikes, right? But otherwise, every single other time, the cost is extremely low, right? It almost looks constant except for these infrequent spikes. But if you take the average, those spikes start to even out. Now your otherwise cost in all the other times, that goes up slightly when you take an average, but it still looks to be constant as even as the size of the data structure grows. As you grow from 10 elements up to 1,000,000 elements, the average cost of all these operations is still going to remain constant. Unlike a linked list, where if you've got a million, go from 10 elements to 10,000,000 elements, then that linear cost is going to go up and up and up and up forever, right? A hash table will stay relatively constant when you look at the amortized analysis of it, okay? So you need a way to determine when should you rehash, right? Rehashing is expensive and you don't want to do it willy-nilly every single time, right? Occasionally you will need to rehash though, and to do that, you generally keep track of a load factor, right? A value used to determine when you rehash, right? And by the way, rehashing could also mean that you are decreasing the size. If you have 10,000,000 elements and you delete 90% of them and you're down to a few thousand elements, right? That means that, well, maybe I don't need such a big hash table anymore. I can downsize, right? Save on memory, basically. And the load factor is generally n divided by m, where n is the number of elements in the table, right? And m is the size of the array. Again, table. Right? An example. You could have n divided by m being 0.75, right? i.e., the table is how full? Oops, not 75%, but 0.75. The table is 75% full. Right? If that happens, then you can say, okay, it's too full. We'll go ahead and rehash so that it is only 30% full. We'll double the size or something like that. Now it's only 37.5% full. Right? Generally, this means that you have a trade-off. This provides a tunable trade-off with hash function or hash tables. Right? The trade-off is time versus space. In other words, CPU time versus memory. Right? In other words, if you have a smaller table, then what does that mean for collisions? Are collisions going to be more frequent or less frequent? If you've got a small table, pigeonhole principle, right? Are collisions going to be more frequent or less frequent? More frequent, more collisions, right? And consequently, it's going to be slower access / insert / delete, right? But another way of looking at this is less wasted space. Right? So small small memory footprint means that you are willing to take more time to do things. On the other hand, if you've got a large table, it's just the opposite. It's a complete trade-off. You have less collisions, or fewer, I should say, fewer collisions, and thus faster operations. But at the same time, if you've got a larger table, what does that mean? All the way back to the beginning? More wasted or used memory. So you've got this time-space trade-off. And that load factor allows you to determine that. There we go. That load factor of 75%, you can tune that. If you're willing to waste more space, then you can tune that down to, if the table is 10% full, we will rehash it so that it is only 5% full, meaning that you're wasting 95% of the space at any one time. But everything is super fast, right? Because the collisions are very, very improbable, very, very low. But at the same time, if you want to say save on space, and we're only going to rehash this if it's 95% full. You're only wasting 5% at any one time, but at the same time, it's no different than having a regular old array. Right? So you can tune that somewhere in between. And by the way, I chose 0.75 because guess what? That's the default load factor in the Java implementation of all the hash-based data structures. You can change that in Java. If you've got a hash set or a hash map or something like that, you can create a new one with and then provide it at instantiation with a load factor. And then you yourself can tune the behavior of it and then do some empirical analysis and find that, oh, we want faster operation, so we'll kick that down to 0.25 because we've got a lot of memory sitting over here. Who cares, right? And you can tune that throughout, right? Yeah.
So memory here, is it RAM or?
RAM, I mean, now you're getting down to engineering questions and details because, yes, it's RAM, but it's also virtual memory. And, I mean, and then you might have a virtual machine sitting on top of actual hardware. On top of that virtual machine, you might have yet another virtual machine, and then you might have a Docker instance. And so memory is like 50 layers removed from what you're actually doing. You could have a Java virtual machine on top of that, right? So yes and no. It could mean RAM, but it just means storage, whatever that means. Right? Okay. So any questions on hash tables? Hashing? Yeah.
So what we mean by the number of elements in the table versus the size of the array or table is we don't mean, we do mean the size of the hash table so far.
Yep.
But then
The size of the hash table.
keep track of an extra, basically like number for how many things we've added or taken away.
Yeah, of course you would still keep track of the size. You put stuff in, that's just basic bookkeeping with a dynamic data structure. You put something in, you increment a counter. You take something out, you decrement a counter. It's really easy, right? M is going to be the size of the hash table, and then suppose that there are only n elements in there, right? So let's just suppose that they're all contiguous here. Then that means it's only, say, 50% full. Right? And this space over here is wasted, but it's available. We can continue putting stuff into it. But if we do, then it becomes fuller and fuller and fuller until the performance degrades, right? As you get fuller and fuller because there's more collisions, there's more rehashing going on, there's more collision resolution, whatever strategy you've chosen there. There are also things called perfect hash functions. For example, if you have all of your elements here, and you know that you're never going to take anything out, you know that you're never going to put anything in, or those operations are going to be so infrequent that you want to optimize for lookup, right? Put stuff in once and then only ever look something up. You can come up with what's called a perfect hash function. That is that you've decided that I'm only ever going to put n things into the table. I will create an array of exactly n size because it's never going to grow, it's never going to shrink. And I want everything to fit exactly in one spot and one spot only. That means I'm going to reverse this design, and I'm going to come up with a hash function that gives me that behavior. That's called a perfect hash function because it perfectly maps each one element to one cell, and there are no collisions at all, and there's no wasted space. That's why it's perfect. It's a completely bijective function, a one-to-one function, and it's on two because there's no wasted space. And it's one-to-one because one element goes to one cell. And that means that you've got perfect recall. You've got perfect lookup on this table going forward for the lifetime of this table. Now, if you ever do need to grow or shrink, that means that you need to come up with another perfect hash function. So you're basically pre-computing and pre-doing all the work up front in order to get this perfect hash table, knowing that you'll never change it once it's created. Right? So lots of upfront costs to come up with a perfect hash function, but lots of savings later on. And again, that's a different types of amortized analysis. If you invest a bit today in, say, the stock market, 50 years from now, you'll have a big payback, right? Assuming that you don't take anything out or put anything in, you always put the stuff in though, right? Anyway, that's another way of looking at it. Yeah.
And whenever we do rehash, like we're taking the things from our old element and we're putting it in
Yep.
the new
Throw
line.
away the old table. Each element gets rehash.
Right, but none of the things from the old element, when we put them back in, none of those will collide with each other because
They might
the
still.
hash is bigger.
There's a smaller probability that there will be collisions, but that probability is not zero.
Oh, okay.
Right? You just hope that it's less because you've made a larger table.
So we might have to rehash
No, you just have to resolve the collisions. If that means linear probing to find an available cell, or if it's chaining, then you have to do it. I mean, if you want perfect no collisions at all, then and you find a collision, then okay, I need an even bigger table. I need an even bigger table, right? It's an arms race, and so you wouldn't generally do that. Right? You would just make it bigger, fewer, with the assumption that there might be collisions, but that's okay because there are definitely going to be fewer collisions.
So it's not a replacement for placing like trees.
No.
Place.
It's just different strategies,
Okay.
giving you different properties, and of course, the complexity of actually implementing them. Okay. All right. Great. Then let me go ahead and dismiss this. Now let's go ahead and start talking about, sorry, I need to come up with the preview. I can only have one preview at a time. There we go. Graphs. This is where it gets fun, right? I don't know if you like fun or not, but or if you think graphs are fun, but they are, because they're really, really easy. You can do a lot of stuff with them. So graph algorithms. So generally, we're going to talk about undirected graphs. Hopefully, we all had graphs from, say, 235, right? You all have had trees before. Trees are just graphs that have, what special property do trees have that graphs don't generally have? They're what? That's, for directed graphs, you can talk about posets, partial orderings. But what is a tree? A tree is an acyclic graph. Right? So in a graph, you can have cycles. What we're going to focus on are undirected graphs, right? So edges between nodes or vertices have no orientation. So let me go ahead and draw a graph over here. Right? So generally, we refer to these as vertices. And then you make edge connections between those vertices. There's one particular graph. Now you can of course draw them so that there's data in those, right? You can draw them so that they're numbered, or that there's some storage, there's some data being stored in the nodes, or even on the edges, right? You could label this as A, B, C, D, and E, and then you could say that it's the cost of going from A to B. Now suppose that costs me, say, $5 what? $5? 5 gallons of gas, right? It's just a measure. It's just a resource measure. 5, right? And then you can have weighted graphs where every edge has some sort of a weight. Unweighted graphs are basically weighted graphs where all of the edge weights are 1 and uniform. It costs you 1 to go from A to B, and then it costs you another 1 to go over to E. All right? So let's go ahead and go back to this graph over here. I won't label them, because generally what we'll do is we'll assume vertices are numbered V1, V2, Vn. Right? Who cares? 1 through n. Right? Now, if you're doing this in an actual program, then you'll want 0 indexing, so 0 through n minus 1. Right? That's perfectly fine too. This is my vertex set. Okay. Note here what variable did I use to denote the number of vertices? How big is the vertex set? N. We generally use n to denote the number of vertices. What about my edges here? So if this is V1, V2, V3, V4, and V5, and I redraw this graph as I had it before, something like that, then how many edges do I have? E will be my edge set. Okay? Now give me one thing in this edge set. Give me one thing that's connected.
V1, V3.
V1 and V3. Right? That's one edge. Now note here that we are using this kind of tuple notation. That's usual. Now in tuples in, say, Python are ordered, but since this is an undirected graph, then the edges are unordered. So you'll see a lot of, say, graph theory folks from math using the curly brackets instead, because curly brackets denotes unordered. Usually in computer science, though, who cares? We'll just go ahead and use the parentheses to denote this. In other words, if I've got A and B are connected, that's the same thing as saying that B and A are connected. You can go with a directed graph, and in which case those are not the same thing, if you really want to, but then you would draw your graph to have orientation, that edge goes from that vertex to another vertex. This edge goes from V3 to V2. And if you want both of them, you would have to end up drawing it back and forth. Right? But otherwise, you can only go one direction. That's a directed graph. We're going to mostly deal with undirected graphs. So let me go back. Right? And those, in fact, are equal. What else is in the edge set? V4, V5? Why did you say V4, V5 instead of V5, V4 since they're the same thing? It doesn't matter, of course, but why did you say that? Nobody would have said V5, V4. Yeah, exactly. You go in the natural lexicographic order, right? And that's the natural way of writing them too. It would be weird if I wrote V5, V4. Right? What else is in there? Dot, dot, dot. Give me one last thing. V3, V4. There we go. How big is the edge set in this case? How many edges are here? 1, 2, 3, 4, 5, 6, 7? Right? In general, we're going to use the variable m to denote that. Right? So we write G is an undirected graph. We write it as a tuple. It's a vertex set and an edge set. Generally speaking, the number of vertices is going to be n, and the number of edges is going to be m. So help me out. How much graph theory did you have from, say, 235? At least this? Say what?
At least this, but I don't remember
Okay.
exactly how much. So.
Okay. All right. So maybe some terminology then. Right. Again, you can have weighted or unweighted graphs. Directed graphs will have an orientation to their vertices. So if I write x, y, then it means you can go from x to y. You can talk about weighted versus unweighted graphs. Right. Each edge may have a numerical weight, right, associated with it, a cost or a benefit. Right. Unweighted graphs are weighted graphs with uniform weights of 1. So what is a path in a graph? Is a sequence of connected vertices. Right? A cycle in a graph, what is that? Is a path that begins and ends at the same vertex. Okay? The length of a path or cycle is the number of edges on it. Generally, we use n to denote the number of vertices. By the way, that's not absolute value. What is that thing? Cardinality. That's a cardinality, exactly. Generally, we use n to denote the number of vertices. We use e or m to denote the number of edges. Right? A graph is a tuple, G equals v comma e, of a vertex set, v, and an edge set, e. So let's talk about some very special types of graphs. for example, what if I were to write, say, k sub n? This is a complete graph on n vertices. So what does it mean for k3, say? How many vertices do I have? 1, 2, 3. And it's complete, meaning that all possible edges are present. So how many possible edges do I have with a K3?
Directed or undirected?
Undirected. Without qualification, we'll always assume undirected. 1, 2, 3, right? So the size of the vertex set here is 3, and the size of the edge set is 3. K4, what does that look like? 1, 2, 3, 4. How many edges are going to be here? Let's start drawing them. 1, 2, 3, 4. Am I done? What else do I need? 5. And then 6. If you don't want to do something like that, if you don't want your edges crossing, you can always try to draw it so that they're not crossing. Okay? So 6 total. K5, what does that look like? 1, 2, 3, 4, 5. So every single one is connected to every single other one, and we've got one more here. Right? Did you count them up as I went? How many edges did we have? 10? Okay. Do we start to see a pattern here? Kn is going to have, by definition, n vertices. What about the number of edges?
Times n minus 1 over 2.
Ooh, you went really fast there. Go ahead and say it again.
N times n minus 1 over 2.
And how did you get that?
Each one connects to one of.
Each no. Well, let's think of it in terms of edges. How do I form an edge?
2.
I take among all the vertices, n vertices, I need to take 2 of them in order to make a connection and for them to shake hands. So among n of them, I need to choose 2 of them to shake those hands. And it's unordered because A shaking B's hand is the same thing as B shaking A's hand. Right? And that's why it's n choose 2, which is equal to this up here. So in other words, at most, for any graph, you can say that the number of edges lies between n choose 2 and what's the lower bound on the number of edges?
0.
0. You can have an empty graph. That's perfectly fine. Here's an empty graph on 3 vertices. Here, it's not an empty graph. It is a graph that has 3 vertices, but whose edge set is empty. You can have that. These are called isolated vertices. You can have a graph with some connected component over here, but an isolated component over here. That's perfectly fine too. You can have any topology you want, and we do use that word. How a graph is set up is its topology. Think about geography. What do we mean by topology and geography?
Isn't it elevation?
Elevation, a relief map, right? It is how the land is set out. With a graph, the topology is how the graph is set out. Okay? So you can talk about graph topology. What about, let's say, paths? Let's go back to that original graph that I had. There we go. A, B, C, D, and E. Is there a path from A to B to C to D? A to B, C, then D. Yep. What is the length of this path?
4 or 3.
There are 4 vertices in it, and to connect 4 vertices, you need 3 edges. Right? Give me another path. A to B to E to D. Right? There's another one with length 3. In fact, I'll go over to C here and make it length 4. What about the following path? A to B to E to B to E to B back to D. This is D down here. Is that a path? Technically, what am I doing? I'm going A to B, back and forth, and then going on to D. Technically, that's a path, but it's not a simple path. We will only be talking about simple paths and simple cycles, right? So you can't have something that goes back on itself on an edge more than once. Now you can have something that goes on a vertex more than once. So for example, you can go from A to B to C, to D, and then back to B, then to E. What did that look like? A to B, C, D, back to B, then over to E. Right? And that you can talk about that path, even though that you visited this vertex more than once. It's simple with respect to the edges. You only traverse the edges exactly once. Right? You didn't go back and forth needlessly. Right? But this does contain a cycle. A cycle between C, D, and B. A cycle is one that begins at one vertex and goes around and then comes back to that vertex. What is the size of this cycle? What is the length of this cycle? How many edges did I traverse to get there? 3. Okay. So is it all coming back now? Okay. Then how do we represent a graph in, say, a piece of code? What are some ways that you've seen before, now that things are coming back? Adjacency. Adjacency what? Matrix? Okay. What's an alternative? A list? Right? You can use maps. You can use sets of pairs of vertices, right? Etc. There are lots of ways that you can do this. Use one data structure to represent another data structure. You do it all the time, by the way, remember? You use a linked list to implement a stack or a queue, right? You use a queue to implement something else, maybe, if you want to, right? A buffer, right? You use a queue for a buffer. So you've got this layering of data structures. How do you do a buffer? Well, you use a queue. How do you do a queue? A linked list, right? How do you do a linked list? It's a series of nodes, right? So you're building more and more complex structures as you go up. Same thing here with graphs. Do we want to see what an adjacency matrix, adjacency list look like? Yes? No? Yes? Okay. All right. Let me go ahead and label these. Same graph as before. All right. A, B, C, D, and E. All we're going to do for an adjacency matrix is associate, put an ordering on all of the vertices. And in this case, it's a natural ordering A, B, C, D, E. C, D, and E. A, B, C, D, E. And each entry here of this adjacency matrix is going to be either 0 or 1. It's going to be 0 if ij is in the edge set, is not in the edge set. It's going to be 1 if ij is in the edge set. Right? So A goes to B, that would be 1. A goes to C, so that'd be 1. Does A go to D? Nope, so 0. Does A go to E with 1 edge? Nope, so 0. By convention, you do not have self loops. That would that's reflexivity. You're talking about posets. That's reflexivity, where all the self loops are there. Implicitly, all the self loops are there. If you're at A, you can get to A at a path of length 0. You're already there. Just stay there. Don't go anywhere. So the diagonal on this matrix is always going to be 0. Or if you need to, for programming purposes, you can say that you could make it 1, right? If you're at A, is A connected to A for some purpose, right? Then you can go ahead and put it as 1. Do I need to fill in this lower diagonal here? What's it going to look like for undirected graphs? If this is an adjacency matrix A is going to be equal to A T. What is that T? I thought everybody took a
It's like
linear algebra.
what's it? Just as a
Transpose. Right? It's symmetric. Right? That goes back to posets, right? It's a symmetric set. That I can go from A to B, therefore I could go from B to A. This should be 1, right? Across the diagonal, these are all going to match. So there's no point in keeping track or maintaining those, unless it's a programming language detail that you do need to keep track of them, right? Or you just change the question. Anytime you ask, is A connected to B? You ask the question, well, is A connected to B or is B connected to A? And then you answer yes, if either one of those things happens. Right? Anyway, what's the rest of this look like? B is connected to A, C, and D, but not E. C is connected to A, D, and B, so there. And then E is connected to B and D, so there. And B, we already got that right. Oops, sorry. This one should be 1 right here. There we go. There's an adjacency matrix representation. What does an adjacency list look like? Each node has associated with it a linked list. That linked list, not linked, is going to contain all the nodes that our A is connected to. So B and C. B will have a linked list containing A, C, D, and E. There we go, ... And you get the idea here. One of them, and I think that I've got some exercises for you to think about here, but choosing one of these representations means that some of the basic operations on a graph, like asking whether or not 2 vertices are connected, become really efficient with random access on an adjacency matrix. They become less efficient with a linked list implementation. But other things become more efficient versus less efficient. For example, one thing that's really, really efficient with an adjacency list is computing the neighborhood of a vertex. So let X be a vertex in a graph G equals V comma E. Right? The neighborhood, neighborhood. In real life, what's your neighborhood? Who are your neighbors in real life?
I forget.
Who's your neighbor right now in this room? John and? Yep, there you go. So the neighborhood are the people that are immediately adjacent to you, right? So the neighborhood of a vertex is the set of vertices connected to X. And we denote it as n sub X. It's all Y such that XY is a edge. Right? Not 3 houses down, right? That would have to mean that you have to take a path from one house to the next house to the next house to the next house to get there, right? That's not your neighbor. Right? In real life, sure, they're your neighbor, right? Be friendly with them. But that's not the neighbor as far as graph theory is concerned. Computing a neighbor, what do you have to do with an adjacency matrix? Go through and find all the ones. What do you have to do to find the neighborhood with an adjacency list? It's there. It's done. It's maintained as part of the data structure. Okay? So, is one better than the other? Or is the other one better than the first one? Right? Who cares? when you actually go to program this stuff, what should you do?
Make both? Or
Do
use
both?
what's already designed?
Okay, so what you Google for graph representation Python, and what comes up is a nice little library called Network X. And when we start next time, I'm going to give you just a crash course on how to use Network X. It's already built for you. You don't have to worry about it. All right. All right. I'll see you next time then.